Good evening, good morning, good afternoon, wherever you are on this planet, and welcome to our SETI Talk. The SETI Talk is a monthly lecture series organized and produced by the SETI Institute here in Mountain View. My name is Frank Marchis. I'm a researcher at the SETI Institute, and today I'm going to introduce to you the talk. So we are a non-profit organization whose mission is to lead humanity quest to understand the prevalence of life and intelligence in the universe. Our lecture series have been running for more than 10 years now, and you can find them on our YouTube page. We have hundreds of talks, debate, discussions, arguments, and fun about science and the extraordinary research done by my colleagues everywhere in the world. So in March, we switched to the virtual world, like almost everybody on this planet. And so today you can follow this lecture from your home using modern technology. So I would like to welcome all our registered guests who joined tonight via Zoom. There is more than 400 of them already. And as well, those who join us from Facebook, YouTube, Twitch, and other social media. So we would like to remind you that we are a non-profit organization, so we depend on funding received by you, by other institutions. So if you want to support us, you can simply follow us, register to get notification when we have a new SETI talk, a new SETI live, or also to simply receive our newsletter. If you have a moment before we start the talk, please let us know in the chat where you are watching us from. Which planet or which city, which state, and which cave somewhere in the world, and we would like to know where we have been reached so far. So tonight's topic of the SETI talk is a bit special, and in fact the idea came from when in December 1st of last year, the iconic radio telescope, the Arecibo of the Arecibo Observatory in Puerto Rico collapsed. A lot of journalists wrote that that was the end of giant astronomy. And in fact, I'm sorry to tell them that it's not true. Giant astronomy is still there and still exists. And in fact, as a proof, we have two remarkable speakers who's going to talk about giant telescopes today. To introduce them, introduce the topic in more details, let me introduce you Simon Steele, our Director of Education and Outreach. And Simon, the floor is yours.
Thank you, Frank, and good evening and good morning to everybody from around the world. And we're getting some places: Sweden, California, Kolkata, India, Liverpool, Mexico, to name but a few. So welcome everybody to the talk. We may well have lost the magnificent Arecibo Telescope last year, but we're entering a new age of giant observatories in astronomy. The Extremely Large Telescope, ELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, and you'll begin to understand those little acronyms and the titles and later on as we move through the talk. They'll all get their first light this decade and are set to transform humanity's view and understanding of the universe. These new instruments will observe at wavelengths from the near-ultraviolet to the mid-infrared, allowing astronomers to address fundamental questions from understanding star and planet formation to unraveling the history of galaxies and the development of large-scale structure in the universe. We're joined tonight by two astronomers whose careers are strongly related to two of these new telescopes to discuss their potential and the status of their development. Rebecca Bernstein of the Carnegie Observatories is the chief scientist for the GMT project, an international consortium where she provides technical and scientific leadership for the design and construction of the telescope. Her research has included high-resolution spectroscopy of stars and extragalactic star clusters to understand the formation and evolution of galaxies. She also studies the stellar components of galaxy clusters and is engaged in various projects related to dark matter and dark energy. Christophe Dumas is the observatory scientist and head of operations at the TMT. Previously, he was in charge of the science operations at the European Southern Observatory Very Large Telescope, VLT, in the Atacama Desert of northern Chile. His scientific interest is in studying the physical and chemical characteristics of small primitive solar system bodies and how they can inform us about the formation of planetary systems at large. So welcome both of you. And I think after the time costs, Rebecca is going to start. So I'm going to hand over to Rebecca to tell us about the telescopes.
Okay, well, thank you for that very nice, very generous introduction. It's really fun to be with you guys tonight and talking about these telescopes. And I'm going to give an introduction. Let me just start by sharing my screen here. Okay, share. There we go. All right, so I'm going to give an introduction that tells you, there we go, not just about GMT, but gives a little bit of the technical information that you need to understand both of the telescopes. And as you'll hear, GMT and TMT are sort of joining forces a little bit. They're two independent projects, but we've been collaborating and working together since these are difficult technical projects. And so this is very much a collaborative talk. We're presenting you to help you understand both of these telescopes. Okay, so I'm going to start with an introduction to GMT, which you can see here against the beautiful background of the video. A quick introduction to what the site looks like. So before we start the video, you see this clump of buildings here, and here are support buildings. This is a residence hall and dining and lodging, and this is a support site for technical warehouse power, assembling the primary mirrors. So I want you to concentrate as I start the movie up here at the summit. So you can see as you come up around the top of the summit, you can see a road leading off to the rest of Las Campanas Observatory. We'll come back to that in a minute, but I want you to see the summit buildings. We've got support buildings for mirror recoding, which happens every year. We've got a utilities building, and now you can see the enclosure of the telescope itself opening. You see the louvers, the openings around the building that help control airflow during the night while the telescope's actually being used. You see the main doors that opened that let the telescope look out. You see the rotation of the enclosure, which allows the telescope to look anywhere in the sky. And I've stopped the video because I want you to notice the scale here. Got little cars down here. This is a door, a human-sized door to the entrance into the enclosure. You see buildings in the background. This is a 21-story tall building. It's about as wide as a football field, and its job is to protect the telescope. And it is a technical engineering feat in itself. So I will restart the movie, and as you see, zooming in here to the telescope itself, you see the extent of the telescope, and it's a little hard to get a sense of the scale. So again, I'm going to point out the railings around the various places on the wall of the enclosure, just to give you a sense of the height here. The telescope is 48 meters from the ground to the top of the secondary mirrors. And I'm going to show you, not the video again, but the primary mirror. So now you can see the primary mirror. We're looking at the 7 mirror segments that make up the primary. These mirrors are shaped so that when they're held in place by the telescope structure, they form a single perfect surface to focus light, even though the mirrors aren't touching. So this primary mirror is more than 2.5 times the diameter of the state-of-the-art telescopes that we have today. Those are 7 8.4 meter segments to give you 24.5 total diameters on the total diameter of the telescope. You can also see up at the top, that yellow structure is the secondary mirrors, and you can see what those secondary mirrors look like in the upper right there. You're looking at them from below. Those secondary mirrors catch the light from each one of the primary mirrors and reflect it back down to form an image in the focal plane. So they're adaptive mirrors, and what that means is they have hundreds of actuators that are constantly readjusting the surface of the mirror, which is a very, very thin, millimeters thin faceplate that allows then the mirror to deform to correct the turbulence of the atmosphere. And this is technology that's been developed over the last decades on the last generations of telescope. And you'll hear that both GMT and TMT are the first telescopes being designed ever to use this technology from the start, which is really key. And let me explain why that's so important. So the reason this is so key is because what you're seeing here is an image that illustrates the limiting resolution that you can usually get from the ground. So the sharpness of an image is usually limited by the turbulence in the atmosphere, which makes the stars twinkle. And compare that to this image, which is what you get from HST. So HST is above the atmosphere, and the resolution of this telescope is limited by the diffraction, what we call the diffraction limit of the telescope, which is the limiting resolution that you get between, caused by the physics of the way the photons themselves interact with the primary mirror. So that diffraction limit actually gets better as the telescope gets bigger. So when we launch the next generation of space telescopes, JWST, we'll see this. So it'll be about 3 times better because the telescope is larger. But this is the best you can do by launching telescopes, because we can't make a telescope. We can't launch a telescope that gets to much bigger diameter than 6.5 meters, not for several more decades. So the next step, if you want to do better, get more light, get sharper images, use more modern instruments on those telescopes, is to build ground-based telescopes. So that's what we're doing with GMT and TMT. Both of them incorporate adaptive optics. And this next image shows you what we'll be able to see with GMT. So you can see that's quite a significant improvement. TMT does something very similar. And you'll hear from Christoph in a minute that TMT is incorporating adaptive optics in a different way. And each of our strategies has its own strengths. And that's part of the beauty of these complementary telescopes. Okay, so now let's talk about the science. So with this giant leap that we're getting in both collecting area and resolution, what are we going to be able to do? So this really is intended to show you that the angular resolution and sensitivity that you get with this next leap really are going to revolutionize all areas of astronomy. So this is meant to be a timeline graphic that shows you the evolution of things in the universe from the Big Bang, the universe expanding, the primordial soup where there's really no particles can even form because the universe is so hot. Then as the universe cools, eventually you get atoms forming, you eventually get to the first stars and galaxies. And then as time goes on, you get to clusters of galaxies, the galaxies we eventually see today, and the stars and planets forming in them. And all of these areas of astronomy can really be revolutionized by being able to see fainter objects with more resolution. So I want to tell you about just one field. Christoph is going to tell you, focus on something else. I'm going to talk to you about extragalactic science. So when we look in the universe, when we look up at the sky, we see galaxies in the local universe of all different scales, all different sizes and shapes. You see a grand design spiral over on the right. You see galaxies colliding here in a cluster of galaxies in the middle. You see a giant elliptical galaxy on the left. And even when we look in places that we think are dark, what you see is that the universe is filled with galaxies. So this is the Hubble Ultra Deep Field. And most of what you're looking at here is a galaxy. There are, I think, 2 stars in this image. Now, some of these galaxies look faint because they're intrinsically faint. They may be nearby, but they're intrinsically faint. They don't have many stars. Some of them are faint because they are at enormous distances from us. And if you focus here on the 3 I've circled and then zoom in those postage stamps, what we're looking at here is 3 galaxies that we already know from the data we've been able to collect are 13 billion light years away. They formed very shortly after the formation of the universe, very shortly after the Big Bang. It's a surprise to everyone when we saw these, how quickly these galaxies were able to form. And what we want to do now is study them in more detail to understand how these galaxies formed, how they've evolved all throughout the cosmic time. And I want to give you just one simulation that shows what it means to be able to see these galaxies with more detail. So on the left, what you see is a simulation from a very complicated computer simulation that includes both dark matter and gas and star formation. And what you see on the right shows you what we would be able to see of that galaxy today. It's taken with the Gemini 8-meter telescope, simulated as it would be seen with the Gemini 8-meter telescope with adaptive optics. This shows you what we'd be able to get with GMT. And it's not just images we want to get, which you can see what a spectacular improvement it is to be able to see that resolution. What we also want to be able to do is take spectra, which tell us distances, dynamics, chemistry, masses, and brings us so much more understanding. So the collecting power of these larger telescopes let you take those spectra because you have more light. And that's really key. And it lets you take spectra of galaxies, planets, stars, and learn so much more about them. Okay, it takes an international collaboration to build telescopes of this scale, and our partners are the universities and research institutions that you see here. So we have 8 in the United States. In Brazil, we have our partner is the state of Sao Paulo. That's been funded at the state level. We have all astronomers in Australia are represented through an institution called the Australian Astronomy Limited. And also the Australian National University is a partner, and then KASI, which is the Korean Astronomical and Space Sciences Institute. And you can see also here the location of the site of the telescope. So I'm going to stop with this, just going to show a nice image of the site as you can compare it to the image we were showing earlier. You can see Magellan there in the background. That's the existing telescope on that at that observatory and where the GMT will be. And with that, I'm going to stop sharing my screen and turn it over to Christoph to tell you more about TMT.
All right, thank you, Rebecca. Okay, so I'm going to talk to you about another giant, okay, that's going to be built over the next decade, which is the 30-meter telescope. Let me try to share my screen. All right. Okay, and let me know if you can actually see that. Okay, do you see okay? Yeah,
looks perfect.
Okay. Thank you. So this is a 30-meter telescope, and this is obviously a telescope that has not been built yet, as it would look like on Mauna Kea, which is one of the biggest islands in the world for doing astronomy, and it's located on the big island of Hawaii. So what's very particular with this telescope is that it is, well, first 30 meters in size, which is very big, obviously, but it has also like a shape which is quite different than the other ones, okay? And the shape of this enclosure, as you see on this picture, is not, made of cubic or big doors that are opening. It is made of a sphere. And actually, the aperture of this sphere, of this circle, is obviously the diameter of the telescope, slightly bigger than that, 30 meters in diameter. And thanks to a rotation on the horizontal axis and on an inclined axis, you can actually point any point of the sky. You can see any target in the sky by rotating the dome, this enclosure, over these two axes. On this image, you actually see the dome itself, but you also see a small building, which is the building where this telescope is going to be controlled as a facility at the summit. I'm going to show you on the next slide another movie, like Rebecca did, a bit shorter, showing you the rotation of this enclosure. And you see actually the telescope pointing on its maybe first target during the night. And then we are going to move closer to the telescope, and you will see the primary mirror, the secondary mirror on top of it, and I will explain to you where the tertiary mirror is located, so we can actually, move the light towards the science instruments. Something to consider is the size of the telescope. As we told you tonight, we are talking about giant telescopes, and at the bottom right picture on this slide, you actually see a series of telescopes. Some of them are already operating today, like the one on the left, which is a very large telescope in Chile, or the one in the middle, which is a Keck telescope, and the other ones on the right, which are smaller on this picture. And you see the big 3 large telescopes that are going to be built over the next decade. The extremely large telescope on the left, 39 meters, the TMT in the middle, and the Giant Magellan Telescope that Rebecca told you about, which is 25 meters in diameter. And you see that the 30-meter telescope, even though it's 30 meters in diameter, is actually very compact in design. It doesn't look so much bigger than the telescopes that are currently being operated today, okay? And you're gonna see in the next picture why. The design of this telescope is such that even though it's 30 meters in diameter and 450 meters in focal length, it's actually very compact, and the size of the enclosure is actually smaller than 60 meters in height. You see how compact it is, the enclosure itself just basically barely fit the telescope and the two platforms on each side, which are going to host the science instrument for this telescope. Obviously, you need science instruments to do science. The telescope is collecting the light, and the science instruments are going to allow you to analyze this light and actually do your science, okay, observing any kind of object in the universe. On this image, you can actually see another section of the telescope where it is inclined. It's actually easier to see the various systems. Don't worry about the naming, okay? I'm going to talk to you about some of them later. But if you look at the primary mirror, obviously it's 30 meters in size. And you see, as we actually saw in the original movie that I showed you 2 slides ago, the secondary mirror that's going to collect the light from the primary mirror and send it to a tertiary mirror, which is inclined. And this mirror is going to send the light, is rotating on its horizontal axis. And it actually can, on its vertical axis, sorry, and it can actually move the light, okay, project the light on one platform on each side, on one side of the telescope, or the other platform where the science instruments are seated. This primary mirror is not a unique piece of glass, okay? It is actually made because it would be extremely difficult. It's actually impossible to do a 30-meter size telescope with one single piece of glass. So the strategy here is a bit different than the one used for GMT. Instead of having one single mirror, we have almost 500 of them, 472 exactly. And these mirrors are smaller in size, they are hexagonal in shape, and they are arranged in some sort of honeycomb. So you can actually pave the primary mirror of the telescope with this 492 mirror, segmented mirror, to make a single mirror of 30 meters in diameter. Obviously, one of the challenges is to have all these small mirrors aligned and phased. We are going to discuss that later tonight. And I wanted to give you also some additional numbers. I told you about 30 meters in size for the primary mirror, made of 492 segments. 3.1 meter is the size of the secondary mirror that you see on top. This one is convex, it's passive, not adaptive, okay? It's a passive mirror. We will probably have an adaptive mirror in a future upgrade of the telescope when it's built. And the tertiary mirror I told you about, which is actually directing the light towards the science instrument, is an oblong mirror, 2.5 by 3.5 meter. We can have up to 8 science instruments as a telescope, 4 on each platform, more or less. And as Rebecca mentioned to you, we will have first adaptive optics at first light. We have a dedicated adaptive optics facility working with laser guide stars that's going to be feeding up to 3 science instruments, and 2 of these science instruments are going to be available at first light. What we call first light is when we start operation of the telescope. So also something to consider is about performance, okay? Rebecca has this wonderful slide where she was showing to you the powerfulness of adaptive optics to shrink the light and get access to the full diffraction limit of a giant telescope, like a 25-meter telescope or a 30-meter telescope in size. What does it mean? That means, like, in terms of angular resolution, which is our finer, our smaller detail you will be able to see in your science image. Okay, we have with telescope of this size up down to 7 milliarseconds resolution. What does it mean? That means that if you hold a quarter, a piece, okay, of quarter, 25 cents in your hand in Los Angeles, somebody with this telescope sitting in San Francisco will be able to see it. Quite amazing, okay? But obviously, we don't only want to take images, we want to make measurements of motion of objects, okay? Motion of stars around a black hole, or motion of satellites around an asteroid, for instance. And we want to see how precise these objects are moving. So that's what we call differential astrometry. And with this telescope, we can get down to 50 microarseconds. What does it mean? That means you hold the same corner in your hand, which is a quarter, and 50 microarseconds is a motion that if you move this quarter in your hand by its diameter, as seen from the distance, a quarter of the distance between the Earth and the Moon. Okay, this is amazing, 100,000 kilometers. So this is the kind of precision we get with these telescopes. So these telescopes, as Rebecca said, these are expensive, they are big, they are complex. We need international partnership to build them. The partners of the TMT are Canada, India, China, Japan, And we have two University of California, University of California and Caltech. In terms of sites, TMT has not resolved the site where it's going to be built yet. We have the main site, which is, as I told you earlier, the island of Hawaii on Mauna Kea. But we have difficulty to access this site due to some opposition of part of the population. And we have also an alternate site, which is La Palma. Okay, so in order to have sites for astronomy, good site for astronomy, you need a site that's dark. You need sites in altitude, so you have a minimum amount of atmosphere to go through for your objects and collect the light. You need a site with a very stable atmosphere. And this is what you can get if you're sitting in the middle of an ocean, like in La Palma or Hawaii, or if you are in Chile, like the GMT, very close to the very cold ocean, which is the Pacific Ocean, and the cold water that comes from the South Pole. And so the combination of this, and obviously a place where you don't have clouds, you have to be above the clouds, makes very good site for astronomy. In terms of science, this telescope, we do any kind of science, not only focusing on one topic, okay, from extragalactic astronomy to solar system, to time domain science, to exoplanets. They will do science in synergy with other observatories, whether they are space or ground, okay? And they will also provide future opportunities to combine the science you can get with the optical near-infrared telescope like GMT and TMT, with future telescope or already existing telescope that are observing at other wavelengths like gravitational wavelengths astronomy or multi-wavelengths astronomy in general. Just to give you an idea about the science, this is an illustration of the planetary science, in this case exoplanet, performances that we can get with a telescope of this size. The first image that you saw, which we had less resolution, was you could actually see an exoplanet orbiting the central star, okay, like this one, obtained at Gemini telescope. And you see the central star is hidden, otherwise you will not be able to see the exoplanet. If you turn on the same kind of instruments with a telescope of the size of the TMT or GMT, you will not only be able to see this exoplanet, but also other planets orbiting much closer to the central star. So you can actually do study of exoplanetary systems from the ground and study their atmosphere. The last slide is about solar systems. This is what I'm doing as an astronomer, so I'm very close to this field. And you can actually see an image of Io, which is a volcano of Jupiter, sorry, a moon of Jupiter full of volcano. This is actually the most volcanically active bodies that we know in the universe. And Pluto below, which is a most distant ex-planet of our solar system, which is now a dwarf planet. Okay, and you can actually see the difference between observing these objects from a telescope from the ground, like a TMT in the middle for Io, and on the right side you see the same image observed from a spacecraft, Galileo, which was orbiting Jupiter. And below for Pluto, you actually see the difference between observing Pluto with HST, 2 cameras, the TMT, and it's one of his first light instruments, and also with the flyby of New Horizons back in 2015. So we can actually do some remote geological studies of these distant bodies without leaving the ground, thanks to these big telescopes. So that's all I have for tonight as an introduction for the TMT, and I'm open to questions, obviously, with Rebecca. Thank you. And I'm going to stop sharing if I can find the window.
I'm going to very quickly share just a couple more slides because, oh, there we go. Because we want to let you know about a program that both of these telescopes are engaged in. And that is the US, we're calling the USELT program. And this is really a joint effort between TMT, GMT, and something called AURA, which is the Association for Universities for Research in Astronomy. And this is really an effort to increase the US federal investment in ground-based astronomy. So, you know, the federal government invests in space astronomy all the time. They've invested in many smaller telescopes, and we are inviting them to get in on the ground floor of these larger telescopes to strengthen astronomy in the United States, both technical and scientific, to increase access and inclusion for all scientists in the United States in the same way that Korea, Australia, Japan, India, Canada have joined in these projects as nations, on a national level. We're inviting the United States, the federal investment in these projects in the United States as well. And it will allow also us to combine the scientific reach of each telescope. And I just want to give you a sense of that increased reach by showing you this map, this is actually a map of the sky shown in a projection that you sometimes see for the Earth. So the sky, in the sphere of the sky, is stretched out into this projection. You see the ecliptic plane there. So the plane of the Earth projected onto the sky is where the equator is on that map. And then the north and south poles over the Earth are shown at the north and south poles of this map. So you see GMT in its location projected at one time on one night. GMT is down here in the southern hemisphere. TMT will be in the northern hemisphere at one of these two sites. And the combined scientific power of the two telescopes has to do with getting this access to the northern and the southern sky. So of course you can't see the star over the North Pole from the southern hemisphere. From the northern hemisphere, you can't see the Southern Cross or the Large and Small Magellanic Clouds. So this gives you access to objects in both parts of the sky and allows collaborations to work on objects in both hemispheres. Also, we can specialize if the two telescopes are working together. We can let the instrument suites be more specialized, the two telescopes. And finally, just more hours on sky for larger collaborations if the two telescopes are sort of pooling and working together. So I just want to let you know about that effort, and it's part of the reason why Christoph and I understand each other's telescopes to the way we do. Part of this collaborative effort. And I'm going to stop sharing my screen. And did that work?
Right.
Yes.
Yes, it did.
All right.
Well, thank you very much, both of you. They're both incredibly exciting projects and really awesome. The largest telescope I've observed with is a 4 meter, and I thought that was big at the time, but now I feel rather sad. You've one of your last slides, Rebecca, shows you a picture of the TMT and the GMT. And it seems that they're both very advanced with similar specifications in terms of capabilities, but a very, very different design concept has gone into that. One's using very large 8 meter cluster of mirrors. One's using, I think, 492. I had to write that down. Smaller mirrors. One has quite a boxy dome. One looks like a big eyeball. Can you say a little bit, each of you, maybe Rebecca first, about the design of these huge instruments and what goes into that?
Well, it's a very interesting question. I mean, both of them are building on some of the successes of the previous generation of telescopes. So sometimes we say that one of the advantages of these large mirrors is that the image quality of the mirror is really is a result of the work you do in the laboratory, and the mirror has the image quality. You make that mirror have a good surface, and that image quality is then baked in. You get good image quality from telescopes with those large mirrors, well supported, and we've seen that in the last generation of telescopes. We've also seen the smaller 1 meter mirrors that make up the primary mirror, as in TMT, tremendously successful in the Keck telescope. And so these are just two very different strategies, which each have strengths for different kinds of observations. And so, if you have a car, maybe you want to have a smaller car that is more fuel efficient and gets better gas mileage and just has 2 people, but the same family might also want a van for completely different purposes. And it's that kind of, different designs have different technical strengths, and the kinds of observations we want may benefit from the 2 different designs in all sorts of ways. And so when you have access to both, you can make measurements of the same kinds of objects and check whether the 2 systems, the 2 different instruments, get the same results. And that lets you eliminate systematic errors in a way which can be extremely important. And we see this again and again with the measurements that led to, for example, understanding the expansion of the universe. Those were made with one telescope, and many, many different telescopes then started to follow suit. Different groups started to follow suit. And you build up an understanding that minimizes the systematic errors by using lots of different kinds of machines. Same is true for planetary work. Anything where it's a really sensitive, careful measurement that's required, different kinds of tools are very valuable. And the same is true of the domes. There are benefits to both kinds of domes. They're both challenging, they're both expensive, they're both big. And I think we're going to find that they both work, but they're going to have different strengths. And I think you don't want to put all your eggs in one basket. Not that any of them will fail, but you want to have the different advantages of all of them.
I won't ask each of you to say which one you think's better. That would be just cruel.
I have to say I've worked on both projects and I love them both.
Okay.
I can maybe add a bit of, on what Rebecca said, okay? And obviously the design is very different, okay, between the two. Both, as you said, Simon, okay, the enclosure itself, the shape of the telescope from the outside is different. And when you get inside the dome, they are also different, okay? But the challenges are the same, okay? That means you have several mirrors that you need to be able to act as a single mirror. Same thing in the case of Rebecca's design for the GMT. You saw like the secondary mirror is not one single mirror, it's several of them, okay? One for each of these primary mirror. So you need to make sure that the multiple images that you are going to collect, okay, are actually forming only one image. And that's a very challenging area in engineering, obviously, okay? So that I would say in terms of building this telescope, obviously, because the purpose of building such large telescope is to get the best image quality possible, this is crucial. You want to make sure that these mirrors are phased and aligned in a way that you're actually providing and producing the best image quality possible. And for the enclosure, it has all to deal with the conditions around the observatory. We mentioned already, it's very important to choose a good site, okay? And we make measurements for that. We have campaigns. In my team, we have people who actually spend decades making measurements all around the world to find the best place to build the TNT. And obviously, when you build this telescope, the enclosure itself is going to create perturbations, turbulences, okay? And you want to make sure that the amount of turbulences created by the enclosure itself is minimum, so you are not deteriorating the image quality that you would get if you didn't have any enclosure, for instance. So that's very important. And you see that two designs are also very promising, very different, but very promising.
Now, was there any, in the terms of the design, was there any sort of computer modeling? Do you construct that these days, or sort of wind tunnel, sort of on the computer? How does that work?
To tell you the truth, there are only very few, good experts in this. Okay, and GMT and TMT are sharing this expert. He works for both projects. Okay, making simulations about the level of turbulences that we are going to get within the telescope, depending on the atmospheric conditions, the temperature, the wind speed, the direction of the wind, where we are pointing the telescope. And you saw that on both of these telescopes, you have what I call like flaps, okay, and openings all around, okay. And you need to, of course, if the wind is not too strong, you need to open these openings so the wind is actually get introduced into the telescope, going through the dome, going through the enclosure, so it doesn't create turbulences. It just laminar flow going over the telescope as much as possible.
I would just add to that the GMT's actually had the airflow around and through our dome analyzed by the Boeing Corporation. And I have often joked to people I've spoken with about the project that if you don't trust Boeing's simulations of airflow, you really shouldn't get on an airplane. So we have done lots of simulating.
That's great. Just to remind everyone who's listening here, we'd love to hear your questions. Please do start writing them into the Q&A. We have Frank and another Rebecca who is going to field those questions to you in a few minutes. So we'll turn over the questioning to the audience. Of course, to build these telescopes, there's you know, there's science, there's engineering, but there's also politics and money. And these are no longer single country constructions. A single country really can't do that. Even the US with its great resources. Say a little bit, you know, about the origins of this. You know, you say you wake up one morning and say, I want to build a 28-meter telescope. Where do you go from there?
Okay, should I start first? All right, let's go. Yes, okay. It's actually interesting to look at the history. As Rebecca said, these telescopes are, the design of this telescope is based on previous knowledge, previous expertise of building other telescopes. And in the case of the TMT, while, you know, University of California and Caltech were building the Keck telescope on Mauna Kea, they were already thinking about the next generation of telescopes. This one was not even finished. It's a 10-meter size, 10-meter size telescope. They were already thinking about, okay, what next telescope in size, in bigger telescope, obviously, we can actually build. So Caltech and California started the TMT, as they did for Keck, but very early on, they realized that you know, two universities cannot afford building a telescope that's going to cost, in the end, more than $2 billion, okay? And so you look around, obviously, and you realize that you're not the only one thinking about this big telescope. Canada was also interested in its own project to build not a 30-meter telescope, but a 20-meter size telescope. The US themselves, not Caltech and California, but the US, you know, at large, we are also thinking about a large telescope, an extremely large telescope. So, you know, you start collecting, you know, this partnership. Japan also was very interested in accessing telescope bigger than Subaru. Japan is operating an 8-meter class telescope on Mauna Kea, and they wanted to have access to a larger size telescope, so that we joined the project. And India and China, who have not access to large telescopes, wanted to be part of the game. Okay, so they also joined TMT. So the partnership of TMT, which is now representing more than half of the world population, if you take into account all these partners, okay, it's quite amazing, is actually required and necessary, it's mandatory to be able to build this telescope. And very early on, I mean, very soon, hopefully, you saw that the US is so far only represented by Caltech and the University of California, but the federal government of the US is also very much interested in joining TMT. And we have actually, together with Rebecca, as you saw in the two slides she presented, we presented the concept of USELT projects to get funding from the US federal government to build both GMT and TMT.
And from start to finish, I was going to let Rebecca say something, but I was just wondering, give us a sort of time scale, you know, from time zero to first light, Rebecca, what are we looking at here?
Well, Christoph was just mentioning, and it's true, that the TMT partnership started thinking about the next generation of telescope really before Keck was fully commissioned. So it is a long time scale. It's not an inappropriate comparison, I think, to think about civil projects like bridges. You know, the Brooklyn Bridge took decades to get done. And these are the last generation of telescopes. I think all of them took about 20 years from the start of their collaborations, thinking about the projects and doing the designs, to actually getting them completed. It's that way for TMT, for Keck. It was that way for Magellan. Same thing for the European efforts for the Gemini telescope, for Subaru, so on. Very similar timescales. And it's taken a little longer to get these projects going, obviously. TMT has had issues with the sites. These become very complicated questions when you get collaborations of these scales. Everyone has to agree. You want to keep, you know, all the partners have critical concerns and needs, and they have to be listened to. And so these are very complicated decisions. And it takes time to raise the money. So I think we've gotten a long, long way. I showed you one slide that shows that GMT has the advantage that we own the site. We're building at the Las Campanas Observatory, where Magellan telescopes already are. They're owned. That site is owned by one of our partners, the Carnegie Institution. And so our construction is already underway, but the complexity of the partnerships and some of the funding and development is an ongoing issue as we're working to get these telescopes built. So I think the timescale from now is of order 10 years, depending, of course, on the details of the funding. But I think that both projects have done a fantastic job keeping their efforts going to this point. These are complicated things, and it's a marathon, not a sprint.
Do you think, we're going to hand it over to the audience in a minute. Obviously, these are very expensive projects. You've got to think about your budget. Are you both happy with what's coming out of this? Did you want a 35-meter telescope, but you weren't allowed to? I mean, what do you feel that the projects are coming to fruition with what you want and not too much compromise with politics and money?
I'm happy to start that.
Maybe we should go there. I don't know.
Well, it's very interesting. Neither telescope has descoped. And I think that's very good. So GMT, we're quantized. We have quantized mirrors. Descoping is, sort of a very difficult question, how you descope something under quantized mirrors. And so we're going for it. And I think TMT could easily, they could start with, a partially complete primary mirror, but they have to build the whole telescope anyway. They have to build the whole structure. And so that doesn't really save that much money in the end. And so they're going for it. And I think that's totally appropriate. And I think we want both of these telescopes, and we want them to work, and we're not compromising on the image quality. That's for sure.
No, and I would say this is a sweet spot in size, okay? Because
absolutely,
you really want obviously bigger than the current telescope, otherwise there is no point in building them. But you don't want them too big for two reasons. Okay, one is the cost; the bigger, the more expensive, but also the bigger, the more complex. Okay. And you want to be able to deliver a full diffraction limit performances of this telescope. And the larger the telescope, the harder it is to get control on the image quality, so you will get access to this full diffraction limit. So really, like the 25-30 meter size telescope is really the sweet spot to build these extremely large telescopes in the future.
Great.
Yes.
Well,
thank you for adding that, Christoph.
Yeah. Well, I think it's time to turn over the questions to the audience. So I'm going to invite Frank and Rebecca McDonald to join in the conversation. I know a lot of questions have come in. So Frank and Rebecca, who's going to start? Welcome.
Okay, so I'm going to start, Rebecca. Is it okay? Yeah? So we have a question here from Knitting. Is asking if larger telescopes give better results. How do you choose how large a telescope should be? Meaning, why is the GMT as large as it is and not larger? And same for the TMT.
So since that was specifically for GMT, I'm going to jump in. So our design uses these very large mirror segments. As I said, the image quality, the quality of the primary mirror at some level is baked in the lab. There's more of the image quality that's created on site, so to speak, with these smaller segments. It's been very, very successful before. We went with the larger segments, just partly because of the history of the institutions involved in our partnership. So both are sensible decisions. We went that way. In addition to that primary mirror, GMT has the adaptive optics baked right into the telescope itself. So our secondary mirrors, primary mirror catch the light from the sky, send the light up, the secondary mirrors catch it and focus it back down to the focal plane of the telescope. Those secondary mirrors are adaptive surfaces. So they are wiggling 1,000 times per second to remove the turbulence in the atmosphere. And the largest we can make individual segments of adaptive mirrors today is around 1 meter in diameter. That's proven technology. We're in the 4th generation of it. We know exactly how to do it. And we wanted to use that technology that we thought was, that we confidently knew how to build. So the TMT has made a different decision that leads to very much higher performance in some respects, but more limited performance in other respects. And the two telescopes complement each other very well. But it's those two decisions that made GMT be the size that it is. TMT, I think if I can answer just because I'm on a roll here, is a sensible size for the structure. When you start getting much larger, you can't control the secondary mirror and the primary mirror on their own. You have to start doing something more complex like the European ELT is doing. And so I think TMT very rationally stopped with the size they did, partly because of the structural limitations, partly because of the optical design limitations. Christoph, I'll let you pick it up from there with more.
Yeah, well, I think this question was partly answered also from the previous question, okay, about why 30 meters, but also in terms of, I mentioned that already, in terms of mirror control, image quality. Okay, both telescopes, both designs are very different, but they need to provide a correction of the shape and position of each of these single mirrors in real time. A telescope like the TMT has 3 actuators below each segment, and there are almost 500 of them. So we're talking about 1,500 actuators just to correct the positioning of the segments, okay, in inclination and in piston, what we call piston, which is basically the position in height of these segments. And you also need to correct the shape because there are 492 segments which have different shape. The shape of the individual segment is different whether it is located near the center or near the edge. And the shape is actually controlled, each of them, by 21 actuators. So we're talking about another factor of magnitude in terms of actuators to control the image quality of these mirrors. And this is possible thanks to building a telescope at smaller size, previously like the Keck telescope in our case. Okay, so we would actually were able to design the systems, understand what were the limitations, and now understand what went wrong with the Keck, for instance, in terms of mirror phasing, and we can actually improve that for the TMT, which is going to have much more minimal segments than the Keck, okay, 492. So it's built up on history, and this is really the right size as a level of technology today to provide the community of astronomers with access to these large telescopes.
Excellent. Sorry, I had the question all pulled up and it disappeared. This question could go to either one of you, I think. Does a single large telescope work better than a collection of telescopes acting as a large telescope, like the Event Horizon Telescope, which acted like a telescope the size of Earth?
You cannot do the same, okay? I come from, as was mentioned earlier on, okay, I was in charge of the operations of the very large telescope array in Paranal, where we could actually have, these individual 8-meter telescopes, there are 4 of them working together as a single telescope, and recreate images. It's called interferometry, by combining the images obtained by 2 of these telescopes in different configurations. We could actually reconstruct an image. Like if you have 2 telescopes, it's like if you're working in interferometry, it's like if you're slicing your image, okay, and you have only one slice of the image. And if you have another telescope, you have another slice of the image. So by having your objects in the sky moving, rotating, you observe them under different configuration. So you recreate the slice, or you have more telescopes to recreate the slice as well. So it's a different kind of observations, okay? But it's also sometimes very difficult to do that, to do this kind of interferometry at optical wavelengths. And it really depends what wavelengths you're looking at. So obviously having 2, 3, 30 meters or 25 meters so next to each other would be very nice, okay? But they would need to be next to each other to do this kind of combination of images with the accuracies that you need.
Excellent.
It's already difficult to build one, okay? So let's not talk about 2 or 3.
So I have a question for Rebecca. I think she can answer. It's a question that we are getting from different people, in fact, from Eugenie Taylor and David Duray. What will be the impact of the constellation of satellites like Starlink and others on ground-based astronomy, and specifically on the GMT telescope?
That is an excellent question. It is not, it's not trivial. It's not irrelevant. And interestingly, there are a few, well, I should say, first of all, that all astronomers around the world are worried about this. It affects, but it's very impactful for some of these survey telescopes, like the Rubin telescope, which is doing a large survey for variables across the sky. That project was called LSST, renamed the Rubin Observatory. For those of you who, for whom the name LSST is more familiar. But any surveys would be affected by these satellites, which will vary in your field of view, because when we look at the sky, we expect it to be stable. So when we look for variables, anything that is varying has a huge impact. So the entire field of astronomy is sort of coming together to talk to these companies and try to minimize the impact that these satellites will have. And there are a wide variety of details of the satellites that really do have a big impact on how much they affect us. So the altitude at which the satellites are moving, the reflectivity of the satellites is a big deal. And so, we're not going to be able to stop this. There's no way we're going to be able to put a complete stop to it. So the best thing to do is figure out how to deal with it, communicate with the companies, minimize their impact. And for example, I know that SpaceX is very receptive, for example, to these discussions. So in some ways, we're sort of lucky that they're at the leading edge of this, because I think they will set a good example for companies to come. But it is a big deal. We are working on how to deal with this, both with the companies, minimize the impact of the satellites, and deal with the impact in how we're observing our observing techniques and in the software. Christoph, can you add to that?
Yeah, sorry, I had an internet outage, so I had to reboot my system. Yes, what I can add, sorry, I might have missed some of the words that you were saying while I was rebooting my system, but there are solutions. Obviously, as you said, everybody is impacted and worried about this, okay, because it will only get worse, okay? That's just the beginning of it. That's a problem. There are ways around it. One is to decrease the albedo, I mean, the reflectivity of the surface of the satellite, so it's not so bright, okay, but it is still very, very bright for a large telescope like GMT or TMT. Another way, okay, is to correct the artifacts created by crossing of the satellites, okay, on the image after the fact, if possible. We are quite lucky because GMT and TMT are not wide field, okay, telescopes. They are narrow field telescopes. So compared to an instrument like telescope like Rubin, or LSST, which is going to be very much more effective than us. Okay, we are looking at like a very tiny part of the sky. So the probability to get impacted by such a satellite is still lower than these large survey telescopes, but still it will happen. So another way to do that is to know where they are ahead of time. So, and we can do that. It's actually easy, okay? Because it has to be known. We know where they are ahead of time, and we integrate that in our system of operations, and we make sure that when we observe any point in the sky, we observe it when we know there is not going to be such a satellite in the field, okay? So it requires ingenuity, okay, but we can actually go around it. But we need to work collaboratively with these agencies who are launching these satellites to make sure that the impact is as small as possible.
I think that was an excellent example of how the two different telescopes do different things in the same way. I gave the exact same answer, and Christoph summarized it in a different way perfectly. So you got the story there.
Sorry if I repeated, but I didn't hear all of your story. Okay, so.
No, perfect. Good example.
Thank you, guys. I think this question could maybe start with Christophe. Would you like to say a few words about the European Extremely Large Telescope now under construction and compare it to these projects?
Yes, okay. So it's a bigger telescope, 39 meter in diameter. Okay, so bigger than any of the two that we described tonight. So that's, size matters, okay. If you have a bigger telescope, you have a higher sensitivity, you can observe fainter objects. And also, in theory, you have a better diffraction limit, okay. That means you can actually observe, you have an image quality with finer details on it. So it's very hard, okay, to beat that, obviously, okay, because 39 meter versus 30 or 25 is a difference. But okay, as Rebecca told you, we are combining our efforts. Okay, we are providing 2 telescopes instead of 1 that can cover the full sky, and 50% of the sky is going to be observed by both these telescopes. So we can actually observe them. The same target, from these 2 telescopes with different instrumentation. So the difference is in how we approach the science we want to do with these 2 telescopes by combining scientific and instrumentation capabilities and to provide more opportunities to science users. Also, what I said is true about a sweet spot in terms of size of the telescope. It's actually easier, even though you have a lower or a bigger size of the diffraction limit, okay, lower finesse of the details, with a 30-meter telescope compared to a 39-meter telescope. You're still better in control. We will have a better control of the wavefront, of the image quality, because our telescope is smaller and we have smaller segments as well than the ELT will have. Okay, so there are pros and cons. Okay, obviously a bigger telescope is better, but in terms of image quality at short wavelengths, okay, we are actually going to do quite well.
I want to add just a couple of technical details to that. Christophe is exactly right. There's a couple of key points that really explain why there's a sweet spot. So let me just talk about those for a minute. So as you get bigger and bigger with these telescopes, it stops being possible to build something that has a simple primary, secondary mirror combination, and especially to get adaptive optics in that system. So when you get to a certain point, so at the scale of the ELT, it's become necessary for them to have a much more complicated mirror system in the telescopes. They have a primary, a secondary mirror. They have a tertiary mirror, which sends the light back up to a 4th mirror. Finally, they have a 5th mirror, and that sends the light over to the instruments and the focal plane. And those 5 mirrors need to be aligned. One of them is the adaptive surface, like our secondary mirrors. And then so that's a much harder telescope to build, obviously. Also, it's a very difficult surface to support. When going from Keck to TMT, people thought it would be a very similar thing to support that mirror. Turns out there are a lot of things that are making just that growth harder, especially in seismic environments like we have in Chile. So the ELT is also being built in Chile. So you can think about how much harder it is to support all of those segments in a seismic environment. That's a big deal. And then there's a whole other issue, which is we need instruments to go on the back end of these light gathering buckets. So the telescope collects light, focuses it down to a focal plane, but then you need something like your digital handheld camera to capture the image and maybe turn it into a spectrum so that you can measure the energy at individual wavelengths. And those cameras, even though they're like your handheld digital camera, they're about the size of VW buses right now on the current generation of telescopes. On larger telescopes, the instruments, those cameras and spectrographs, have to get even bigger. And there is definitely a sweet spot in those instruments. So if you make if the instruments have to be bigger than they currently are, it gets impossible to buy the glass in the scales you want. And so that forces the instruments to be sort of out of scale with the rest of the telescope. And so it's not that it's impossible to make instruments that work on a larger telescope like ELT, but you have to start making different compromises in the design of the instrument versus the telescope. And the way the two then work together is not the way it worked on the last generation of telescopes. And so you're buying different sets of compromises as the telescope gets bigger and bigger. And I'm certain that ELT will be a success. I'm absolutely certain, but it might be harder to commission, might take them longer to get to the image quality that they want. And it's definitely going to be harder to build the instruments, much, much more expensive, and it's going to take them longer. It's just always harder to build and takes longer to build larger instruments. So GMT and TMT will be more nimble. We'll be able to build different kinds of instruments that we want to use faster. We'll be able to incorporate different technologies faster. And this can be a significant advantage. And our instruments will perform, I'd say, better for their size. And so, there really is a sweet spot. You don't want to build something that starts being diminishing returns. And so I think both GMT and TMT are very happy with the compromise we've made in what scale we are.
Frank, I think we have time for one more question.
Okay, so I heard I have one more question, but I have two very interesting questions. Okay. So what I'm going to do, I'm going to say the two questions, and I'm going to ask Christoph and Rebecca to choose the one they want to answer to, okay? So first question is, will we be able to record the spectra of exoplanet with those telescopes? And the second question is, if we spot another Oumuamua, will you be able to study this one with you large telescopes, and what kind of information will we get about those asteroids, comets coming from another solar system?
I like both of them. Okay, so
Christoph, since the solar system science is your thing, why don't you answer that one?
Okay, well, why don't I answer both? No, I'm just kidding. Okay, look, objects like, coming from outer space, okay, not from our solar system, we can observe them better with a bigger telescope, obviously. And a telescope like the TMT and the GMT also, we'll be able to follow these objects, okay? The harder is to detect them early on, okay, as early as possible, so we can actually have a lot of time to study them with the instrumentation that we have available as a telescope. So, in some cases, they are only visible a very short amount of time. So you need to make sure that you're there and available to point your telescope and observe them. And TMT will be very good, and I like GMT as well. In time domain science, we will have a process in operations to actually accept target of opportunity. That means when we observe and when we discover such interesting targets, we actually stop whatever we're doing, okay, and observe them, okay, for the community and make the data available. Obviously, okay, like Planet X, for instance, okay, this telescope will be very good at characterizing their surface properties. So, yeah.
Okay. Thank you very much for all those questions that came in. Sorry, but we can't get to all of them. We get many more questions than we can possibly answer. But I just want to wrap things up tonight by me asking each of you, Rebecca first, and then Christoph. Rebecca, you're a galactic astronomer, and Christoph, you're a planetary astronomer. You've just got hold of this brand new telescope. You've got the keys. What will you go in and observe, and what do you hope to discover about it? So we'll start with Rebecca. What's your choice of observation?
Well, I can tell you what I think about today, but I just want to remind everyone that all of the Nobel Prize winning science, all of the most exciting things that were done with the current generation of telescopes were not in the science cases for those telescopes. So I think that the most exciting things we're going to do are not things that we are not addressing questions that we know to ask yet. So when these telescopes get done in 10 years, it may be the case that we start out answering the questions we can think about now, but very, very shortly thereafter, We're going to be answering questions that we have not thought about yet. And I think that, honestly, is the most exciting thing about these telescopes. It's the open discovery space that they will bring with this resolution and sensitivity. Now, that said, if I had to say today what I'm going to observe, the ability to collect light from individual stars and individual star clusters in nearby galaxies and clusters of galaxies to understand in detail how they have formed, I think is extremely exciting. So I would take spectra of clusters, unresolvable clusters of galaxies. So clusters, sorry, not clusters of galaxies, clusters of stars that look like points, that look like single stars. We'll be able to get spectra of those in nearby clusters of galaxies. And I think that will be very exciting.
Christoph.
Okay, so I'm actually glad of the choice I made as the previous question, because now I can actually answer the other question. Okay? So if I was lucky enough, okay, to be still around, and hopefully I will be, okay, and observe with the TMT at first light, I would point it, and I entirely agree with what Rebecca has said, okay? I think in 10 years from now, we have another, space of discoveries to us, okay? And we don't know what we are going to observe and what kind of discoveries we are going to make. But based on today's facts, I will actually point these telescopes toward an exoplanet which is known to be orbiting in a habitable zone of its star. Hopefully this exoplanet will not be too large, will not be too small, okay? And, I will take a spectrum with one of the instruments that we have available with adaptive optics. That will enable us to separate the light from the star and just concentrate on the light coming from the exoplanet. I will take a spectrum of the atmosphere of this exoplanet, and I will look for features of biomarkers, because we know that if we found molecules in the atmosphere of exoplanets, a combination of CO2, ozone, methane, oxygenated nitrogen, all of this, okay, all of this will point to probably having life sustainable on this planet, and discovering life in another planet would be really fantastic. So that's what I would do. And if I cannot do it on the first planet I observe, I will keep searching.
I think that's the philosophy here, is that we really don't know what these telescopes will be looking at, because they are going to make the discoveries as every generation of bigger telescopes has done. What it becomes famous for are things that you didn't even know existed, or didn't know what they were before you started looking. So that's where the pushing the boundaries of discovery are, and that's why telescopes like this are really, really needed to push the envelope of our understanding of the universe. Thank you so much. Rebecca, do you want to add anything to that?
No, I just said, well put, well put.
Thank you, Rebecca. Thank you, Christoph. Thank you to our entire team behind the scenes, Frank, Beth, Barbara, the other Rebecca McDonald. Thank you, everybody, for tuning in and watching. Please do check out our website, SETI.org, because it'll have information on the work that SETI scientists are doing, and also information on the next SETI talks, which will be next month. Frank, do you want to say farewell? Any passing words?
No, it's all yours.
It's all mine. Well, thank you very much. Well, I then had the power to wrap up this meeting. Have a wonderful evening, wonderful morning, wherever you are on this planet. And please do tune in next time for SETI Talks when we are back. Thank you very much, everybody, and good night.
Bye-bye. Thank you.
Thank you very much. It's been fun.